My name is Darlene True-Christ. I'm the Community Engagement Manager for the Ocean Observatories Initiative, and thank you all for joining us. We really appreciate you taking the time and having the interest in OOI to participate. I hand it over to Al Plueddemann, who will be the moderator for the session. Al is the PI for the coastal and global scale nodes for OOI. So over to you, Al.
Yeah, thanks, Darlene, and thanks everybody again for making the time for this. I know your schedules are full. There are kind of three goals that I saw for this session. One is to provide the presenters with a forum to expose their research to a like-minded audience. Another is to do that in a little more relaxed forum than the formal AGU talks. They tend to be rapid fire, and the next speaker goes and you maybe don't have much time to interact. And so please, presenters ask each other questions, the audience ask questions of the presenters. We're kind of here to hopefully discuss a little bit and not just not simply present. And in that discussion kind of brings to the third goal, which is we'd like to look for ways to improve and enhance the synergy between OOI and OSNAP. Both programs are constrained. Obviously, there's not, we can't reinvent things. We can't do anything maybe really major, but there might be some win-win ideas on the margins, that we can think about that would benefit both programs. And you all and our speakers and the audience as well are kind of the boots on the ground, trying to do this in real world. So your ideas are certainly welcome. So with that, I think we'll just go right into it with our first sort of short presentation, which I believe is from Nick.
All right. All right, I assume you can see that okay? I'll take that as a yes. All right, so I'll be discussing some past work, ongoing work, and a little bit of future work, all very quickly on looking at pathways of fresh water around Greenland and also around Labrador, the Labrador Shelf as well. So my name's Nick Foukal. I'm from the Woods Hole Oceanographic Institution, and this was actually this summer's cruise. This is a picture of the Armstrong along the southeast Greenland Shelf from this past summer, and special thanks goes to the OOI team for allowing me to piggyback onto their Irvinger cruise this past summer. So we added 2 days of ship time and were able to deploy some drifters and floats along the East Greenland Shelf. So the motivation for this work is sort of stems from the idea that meltwater from Greenland and also fresh water from the Arctic could potentially be having a pretty profound effect on the large-scale North Atlantic circulation. And to illustrate this, this is a global map of sea surface density. And what you can see up around Greenland in the subpolar North Atlantic is this really dense water that's outcropping to the surface. And it's really important because it's ventilating these deep isopycnal layers of the ocean. And so there's the potential, or we know that the Greenland ice sheet is melting, and we know that there's some fresh water coming from the Arctic into this region, and it has the potential to stratify the subpolar North Atlantic, reduce convection, and slow the overturning circulation. And to give you a little bit of an idea of time variability of this is a time series from Jonathan Bamber's 2018 paper looking at the freshwater flux. This is the black curve from 1958 to 2015 coming from Greenland. So it's the freshwater from Greenland. And you can see this pretty rapid increase from the 90s into 2000s. And so there's definitely evidence to support this idea that this could potentially be happening. That the freshwater flux from the Arctic is a little bit less constrained or less well constrained at this point, but that's something we're definitely interested in. And so from a paper that came out last year, well, I guess I should back up and say that we know that this fresh water from Greenland in particular is not just going out like the ice cube that I depicted prior. It's getting caught up, all this fresh water is getting caught up in the circulation around Greenland. And in particular, there's a very strong coastal circulation, which I'm showing here in the pink arrows. So the pink arrow comes down from Fram Strait along the East Greenland Shelf. And this coastal current has been documented pretty well along the Northeast Greenland Shelf. That's the solid arrow up here. And then also on the Southeast Greenland Shelf down south of Denmark Strait. But in this work, we were interested in whether it connects across Denmark Strait. And so we used data from 6 different research cruises. These are Bob Pickart's research cruises from 2003 to 2018. And we looked at the shipboard ADCP data as well as the CTD data, and we integrated those velocities down to a certain isohaline or a certain salinity surface to look at the pathways of fresh water around Denmark Strait. And we can get a sort of a glimpse as to where this fresh water is going around Denmark Strait. But these are all snapshots. And so we coupled this with looking at an ocean circulation model that's sort of a regional model of the Denmark Strait. And we ran Lagrangian trajectories in the model. In particular, we seeded them down here at the southern line and ran them backwards in time to figure out where they were coming from. And the overall result from this paper was that the coastal current does connect across Denmark Strait, but that it's very connected to the shelf break jet, which is this current that goes along the shelf break, this orange current. And so from a plumbing perspective of oceanography, we kind of connected the dots across Denmark Strait, but I was kind of curious as to whether there is actually a continuous pathway or if this coastal current is the water is constantly being flushed offshore. And so to get at this, we looked at some surface drifters from the International Arctic Buoy program. These are essentially mini weather stations that are mounted on the ice in the Arctic. And they've been up there, this project's been going on since 1979. So there's quite a bit of data from it. And a remarkable number of them cross through Fram Strait, southward through Fram Strait. And so for this, we outlined this region on the shelf in the Northeast Greenland Shelf around Fram Strait. And we counted all the trajectories that cross this region. And surprisingly, they had this remarkably coherent pathway all the way down to Cape Farewell. And if you contrast that to the 59 drifters that crossed a similar polygon just offshore the 500-meter isobath, these trajectories are sort of more reminiscent of what you expect from a kind of a spaghetti plot of Lagrangian data. They just scattered everywhere, especially offshore into the Nordic seas. And so we think that this freshwater pathway, or this pathway for the drifters, is much more connected to the convection in the Greenland seas or the Nordic seas, rather than this pathway. Potentially, this coastal current pathway is very coherent and could bring this fresh water down to the subpolar North Atlantic from the Arctic. So the open question here was, well, what happens to this fresh water as it rounds Cape Farewell? And so we wrote a proposal. This is with Renske Gelderloos at Johns Hopkins and Bob Pickart at WHOI. That got funded to deploy surface drifters and profiling floats along the Southeast Greenland Shelf. And here I'm just showing a little cut through, sort of vertical slice of the velocity from a model. This velocity is coming out of the page at us. And you can see that we were interested in deploying surface drifters up at the surface, and then profiling floats, which would sit at 100 meters and then profile to the surface every 6 hours or 4 times a day to give to relay their information to satellites, which we can then look at. So that was what we were doing this summer on that picture that I showed you on the OOI Irvinger cruise. And here's an animation of these surface drifters. So all told, this summer we deployed 38 surface drifters, and that's these circles. 12 of them had CTDs on them, and that they're shown, the salinity is shown by the colors. And then 26 of them did not have CTDs. That's the black dots. And then the magenta squares are the profiling floats. So they're sitting at 100 meters, and then every 6 hours or so, they come to the surface, relay their information, and go back down. And we were really interested in Cape Farewell because this region, or at this area, the orientation of the winds changes with respect to the coastline. And so all along the East Greenland shelf, there are northerly downwelling favorable winds, which help to keep that fresh water up against the coast. But at Cape Farewell, that's not necessarily the case. And so we thought that a lot of this fresh water would come off the shelf, but surprisingly, we actually found a remarkable number of them. The vast majority of these drifters and floats stayed up on the shelf around Cape Farewell. That's partially due to the winds that we experienced, but it seems to be pretty robust from what we've seen so far. So we're in the process of deciphering this data. As you can see, this was pretty recent. This is past summer, so we're looking through those data and trying to figure out more compelling stories to tell about what actually was going on, and also eventually using these data to validate the model that we're running of the region, so then we can sort of broaden the temporal and spatial scope of these drifters. We're also going out this next summer to do it again, do another round of deployments. And so I also want to touch on this other project that we just got funded to deploy 4 moorings in the Labrador coastal current. So this is on the Labrador shelf, looking at the Labrador coastal current. This is marked here in red. And so we're going to have 4 ADCPs, current meters, to measure the integrated transport of this coastal current, as well as 3 SALP moorings. And I'll explain what those are in a second. But basically, the idea is we want to measure how much fresh water is coming down the Labrador coast, and then also what is its fate as this coastal current, or downstream of Hamilton Bank in particular. It's not very well known whether this coastal current circulates around Newfoundland or if this fresh water comes off the shelf. And we have some, or a hypothesis, I guess, is that this water does come off the shelf. And so I mentioned these SALP moorings. These are moored cylinders, essentially, that hold surface drifters at a fixed location, and they can be pre-programmed to release the drifters on a schedule. And so here we're going to have 40 surface drifters that will be releasing into the coastal current to track its fate and figure out where this fresh water is going. And I should mention that this is a project with Dan Torres and Amy Bauer, who are both at WHOI. So I will end there and happy to take any questions.
That's great. Thanks, Nick. That was good. I guess we're looking for probably raising the hands for the participants is maybe going to work best. And while people are thinking about that, maybe I'll ask the first question. It might be almost reiterating something you said, but just to be clear, that I was trying to watch the wind in your kind of inset there.
Mm-hmm.
Like there were pretty strong offshore winds and developing tip jets, and yet the drifters seem to just go right around the corner. Am I kind of interpreting that correctly? Was that surprising?
Yeah, so but you're absolutely right. So initially, you can see on the top right, these are the winds. There's actually a mini tip jet right there, some upwelling favorable winds. And we do see some offshore movement of the drifters initially. And then some downwelling favorable winds develop. You'll see in a second. Right here. This is right when we were deploying our second set of deployments. Got a little nasty on us. And all that water shifted onshore. You can see quite a few of these drifters went up into the fjords, for example, and this coastal current was really energized pretty far inshore. And so, yeah, definitely it responds to the winds. And so that's one of the reasons for looking at the model, is to generalize beyond what we can observe directly with these drifters.
Fascinating. Yeah, there's a question in the chat from Jamie Palter. When will the Labrador Coastal Current Array go in the water?
So it's supposed to go in this summer. We got delayed because there was lack of ship time. So the plan is summer 2023.
Great. And I don't see any other questions. Darlene, if you're maybe monitoring it better than I am, do you see any others?
No, I think everyone has had their questions answered. Thank you.
All right.
Great. Well, let's move on to the next talk. And I think, Darlene, hopefully you remember who it is. I don't.
It is Nora Fried.
Thank you.
I'm sharing. Do you see it full screen?
That looks good.
Perfect. Give me a second. Yes. All right. Yeah. Hi, everyone, and thanks for inviting me. I will present today work we recently submitted to GJR Oceans about the role of the Irvinger current in the Irvinger Sea northward transport variability. And I'm doing my PhD together with Femke de Jong as my supervisor at NIOZ in the Netherlands. And I will start with showing you the data we're using. So we're using mooring data from the Osnep East Array. They sit on the western side of the Reykjanes Ridge, and we use hourly data from 2014 to 2020, and here we're actually using the monthly averages. And we're combining those mooring data with ocean reanalysis data from the CMEMS Global Ocean Model from 93 to 2020, which is also a combination here of reanalysis and forecast data. And what we want to find out in this study is we want to investigate the Irvinger current's transport variability on both decadal and interannual timescales. And I want to start now with showing you a mean section along that green line you see in the figure. So in this figure, you see velocities, and everything that's red flows northward and everything that's blue flows southward. So we start on the right side of the figure. You see the Irvinger current, which is a surface intensified current with a two-core structure. And then on the left side, so towards Greenland, we see the southward flow of the East Greenland Irvinger current, and then the cyclonic circulation of the Irvinger gyre, which we here call the convection area. So the two different water masses we have here are cold and fresh convective water mass in the convection area, and the warm and saline water mass of the Irvinger current. And one of the main findings from this already is that we looked at the mean transport across that section, and we found that the Irvinger current is responsible for most of the transport across that section. So 11.6 sverdrup from the Irvinger current, whereas the convection area is only responsible for 7.5. The area in between reacts a bit differently, and here we only find 1.1 sverdrup. This circulation, if you look at both the isopycnals and the mean sea surface height above, is reflected in both those slopes. So we have a sea surface height minimum in the central Irvinger Sea, and then the sea surface height is increasing towards the east, with the strongest gradients in the convection area, and the strongest gradient over the Irvinger current, and the second strong gradient over the convection area. And what we now wanted to find out is we wanted to look at how this mean situation changes within the 28 years of data we get from the reanalysis model. So this figure is a bit complicated. I will talk you through. So we'll start with figure A, which shows the volume transport from the Irvinger current for both reanalysis data in green and our mooring data in black. And first of all, you see that the transport is very variable for both of the different measurements, which is nice because they compare quite well. And then, of course, what you can also see is that we have a strong decrease from 93 towards until 2011, and then an increase from 2011 until the end of the time period. The decrease is weaker than the increase, and this increase towards the end of the time period is also supported by the mooring data, but not as strong as what we find from reanalysis data. And in total, if we now look at figure B, we see a decrease in the volume transport over the whole time period, and that goes along with the decrease in the sea surface height difference. If you remember from the slide before, the velocity is reflected in the sea surface height. So the sea surface height difference here is between the sea surface height minimum in the central Irvinger Sea and the maximum on top of the ridge. And what we find here is correlation of 0.33 between both time series, and that increases if we take the Irvinger current boundaries only for the sea surface height difference to 0.73, and both are statistically significant. And from this now, we wanted to find out which side of the which side is having more influence. So if we look at the last plot, this is the anomaly to the mean for the sea surface height minimum and maximum. And basically what you can see from this is that most of the changes are coming from the sea surface height minimum. So for the time we see a decrease in transport, we also see a decrease in the sea surface height difference, which is mainly caused by an increase at the sea surface height minimum. And then we see the opposite for the increase. So changes in the sea surface height difference drive changes in the volume transport of the Irvinger current. And we now wanted to look at the beginning of the time series where we had very strong transport, so the early 90s, and then the time where we had minimum transport around 2011 and 12, and then the end of the time period where we have more or less intermediate transport again. And this is what you see here. So I'm showing here velocity sections again. On the left side, you can see the anomaly to the mean for the respective time period. And on the right side, you see the mean focused on the Irvinger current only. And you can already see that we see quite some differences for those different periods. So very strong and intensified Irvinger current for the early 90s, and then a weaker and even a return flow in between the two cores for the minimum transport, and then a more or less, intermediate or mean situation towards the end. And if you look at the arrows I draw, you can in the anomaly section, you can already see that the slope of the isopycnals, so the lines of constant density, changes. So during years of very strong convection, we see strongly doming isopycnals with the strongest gradients over the Irvinger current, and that then responds in very strong transport. Whereas during 2011 to 13, where we had weak to no convection, we nearly have horizontal isopycnals and minimum, and that results then in a minimum transport. And towards the end of the time period, we had stronger convection again, doming isopycnals and strong transport. And we also did an analysis that shows that it's not only restricted to the section I'm showing here, but also true for a broader, for the broader Irvinger Sea. And I want to show now some results from our mooring array as well. And again, I will talk you through that figure. So what you see on top is volume transport from our mooring array of the Irvinger current, together with the absolute dynamic topography difference from the boundaries of the Irvinger current. And here we also correlated the time series, and we found a significant correlation of 0.48, which is indeed a little weaker from what we found for the reanalysis data, but the reanalysis data is probably higher correlated because of it's necessarily coupled to the model physics, whereas here we have independent measurements. And I want to focus now on the strong transport time period in 2019, where we had a maximum transport of 20 Sverdrup in August, and also the mean transport was, we had higher than mean transport for 5 consecutive months. Figure B shows the absolute dynamic topography of August 2019 compared to the mean with the dashed lines. And as I showed you from the very beginning, you can already see that the gradients here are changing, and this then is reflected in the velocity field below. So we see a very intensified western core in the anomaly section below, and a weaker current at IC2. And what we suggest from this only is that these changes are probably caused by mesoscale activity within the Irvinger current boundaries. And on the last panel, we are showing the sea level anomaly from satellite altimetry, where you can see that we have increased sea level anomaly between IC1 and IC2, which further supports then our guess that this is actually caused by an anticyclone that sits in between our mooring array, and probably even a cyclone next to it. Sorry. So this shows that basin-wide to local changes in the density field contribute to the transport variability at different timescales. And yeah, just to finish off, I'm showing that figure again, where we tried to answer what we tried to answer with this study was how can we explain the transport variability? And basically the main findings are that the Irvinger current is actually the major contributor to the northward volume transport. And that we did see this decrease from the early 90s to 2011, which was followed by an increase. And as I just said, that basin-wide geolocal changes in the density field contribute to the transport variability on very different timescales. Yeah, thanks a lot, and I'm happy to answer questions.
Thanks, Nora. That's very interesting. I have a question. It might be my own lack of understanding, but I would have thought maybe you need this. Could you say a little more about the reanalysis data? I would have thought they would have used SSH in the reanalysis, and so I was surprised to see that the correlation wasn't that good. But there's probably something I'm not understanding about that.
So, so in reanalysis data, they are using sea surface height, and this comes from satellite altimetry as well. That's right. But I think the difference is that they are in the model, both of the variables, so both volume transport and sea surface height are coupled just because it's a model, you know, because everything goes into the model, whereas here, or whereas for the mooring data, the moorings measure on an hourly time scale, whereas the satellite only comes over every 10 days, and then it's a smoothed out product. So I think that's one of the reasons why it's yeah, why the correlation is not that high.
I see that. Yeah,
I think it's also not that low. But
right.
yeah.
No, that's fascinating, actually. Thanks for that. So there was a question in the chat from John Trowbridge. He says, I understand that the changes in density difference drive the change in transport, but he wants to have you unravel it one more layer, and he asks, what drives the change in density difference?
Yeah, I think that's a very good question. So what I'm showing here is I just didn't have enough time to show that. So that's the temperature anomalies on top for the 3 respective time periods, which shows that we had a very cold situation in the early 90s, and then a warm situation during the minimum transport. And which was not uniform compared to what happened in the 90s, and then the 2018 that's a bit more a bit the same to the early 90s. And the one below shows the sea surface height anomaly, and that also shows that the changes that happen along that array are not limited to the section only, but yeah, are true for the whole Irvinger Sea. I'm not sure if that answers the question.
I think that certainly helps. I think that points to that change in temperature anomaly is pretty dramatic.
Al,
I hope you guys don't mind. Yeah, go ahead.
Sorry, Isabella has her hand up.
Okay, yeah, go ahead. Unmute. I assume they can unmute and ask.
Yes. Thanks, Al. And actually, my question is kind of similar to Nick's in the chat here. So Nick is asking, why does the Irvinger current have 2 cores in the 3rd period versus a single core in the 1st period? I think related to that, I was wondering how the Irvinger gyre fits into this. So is the Irvinger gyre that 2nd core, or how does that fit together?
Well, first of all, I really like the question, because I think we're still struggling with whether we should call it a 2-core current or not. So that's definitely something we're going to look into. So I think what we think at the moment is that the eastern core is very stable. That's what we see from our data. Also, if we look at velocity sections, whereas the western core, and maybe that's also what I showed for this extreme month, is more a meandering something with a lot of mesoscale activity. But it's definitely, so because you said if it's connected to the Irvinger gyre, it's definitely separate to the northward flow of the Irvinger gyre. Yeah, and I think I missed, there was another part of your question, was there?
No, I was mostly just curious how the Irvinger gyre fits in, because that's basically at the level of OOI, right? That northward flow. Okay.
That's right.
Thank you. Great talk.
Thanks.
All right, thanks, Nora. I guess any other hand, for some reason, I don't see the hands, Darlene, but any other hands up?
Nope, that everyone has had their question answers. Thank you.
Okay, great. Well, why don't we move on? Yao, I think you are next up if you're ready, and we're interested to hear.
Yeah, let me first share my screen. So do you see it in full screen mode?
Looks good.
Great. So then I will start. Hi, my name is Yao. Thank you very much for inviting me to this OOI and OSNAP in a North Atlantic session. So my today's talk will based on a publication that has been published last year. So the title of this publication is A Stable Atlantic Meridional Overturning Circulation in a Changing North Atlantic Ocean since the 1990s. I'd like to thank my co-authors for their contribution. Before I start my introducing my research, I'd like to give an overview about how OSNEP and OOI are integrated with each other. So as you could see that on this slide, it is a section along the OSNEP line, and the vertical lines with dots are the individual moorings with the different instruments attached. And here are the two OOI moorings that has been integrated in the OSNEP calculation. It measures temperature and salinity all the way through the water column, and it is not just used as an temperature and salinity mooring, but also used as a geostrophic mooring that contributes significantly for calculating the transport in the Irvinger basin. All right, so let's move on. So I guess we all know what the overturning circulation is. So the overturning circulation actually in the real ocean, it is a three-dimensional and complicated system. But when we name it as the meridional and overturning circulation, we try to simplify the three-dimensional circulation system into a two-dimensional view, into a meridional and vertical plane. So in general, in upper ocean of the upper ocean water in Atlantic is warm and saline, and this water mass moves all the way from the South Atlantic, crossing the equator and towards the pole. And this upper ocean water carries a large amount of heat northward, and on the way, the heat is released to the atmosphere, and the density of the upper layer water becomes larger and larger. So eventually in the subpolar Northland region, the surface water density becomes large enough and the water sinks to greater depth and then returns southward as a cold and deep flow. So in this process, a large amount of heat and freshwater transport are involved, and therefore the AMOC is very important for the global climate. A very classical way of viewing the Atlantic meridional overturning circulation is through the meridional distribution of water masses. As an example here, it shows the meridional section of salinity along this section shown here. So we could see that from the salinity distribution, we could identify different water masses. For example, in the surface, we have the very salty subtropical underwater. And then beneath that, we have the northward moving Antarctic intermediate water, which is very fresh. And then below that, we have a southward moving North Atlantic deep water as the lower limb of the AMOC. And at the very bottom, we have the northward flowing Antarctic bottom water. So because the very close link between water mass distribution and overturning circulation, it is generally expected that hydrographic property changes are connected with the overturning changes in the same pace. So in this talk, we can explore that together, whether it is the case. we know that the climate is changing, and as oceanographer and climate scientists, we are of course very interested in knowing how the AMOC has changed and how will the AMOC change. So as stated in the IPCC report, the AMOC is likely to weaken in the coming century. And indeed, we do observe quite substantial changes in the water mass properties. As example shown here is we observe in recent years a record-breaking freshening events in the subpolar North Atlantic, as shown in the lower few maps. So the question immediately follows is, do we also observe a substantially changing AMOC in association with such a dramatically changing water mass properties? And to answer that question, we started to explore the hydrographic section data. There are certain benefits of using hydrographic section data. First of all, we can go back to at least the beginning of the 1990s. That is longer than, for example, the existing area observations, say the rapid observation started only from 2004. And another benefit is that when we use the hydrographic section data, we automatically have the water mass property information, and then we could compare directly with the AMOC estimation from the same hydrography data. And so here we use 3 hydrographic sections. The first one is the Labrador section that focuses on the Labrador Sea. The second one is the eastern subpolar North Atlantic section that focuses on the eastern part of the subpolar basins. And finally, we also have the subtropical section that goes along the rapid line. And you could see that all these 3 hydrographic sections are repeated many times and located in the near the position of the existing area observations. And these area observations are provide very important information for validating the hydrography-based overturning estimates. Before showing you the overturning estimates, I'd like to first give you an impression about how the water mass properties have changed over the past few decades. So here I use salinity in the subpolar North Atlantic as example. In the upper panel, it shows the salinity difference between the 2 different decades, between the 2000 and 1990s. And in the lower panel, it's the decadal salinity difference between the 2010s and the 1990s. The 1990s is used as a reference here. We first could see that in the upper layers, in the eastern part of eastern basins, these water mass first from the 1990s to the 2010s became very salty. And then in the more recent period in 2010s, this water mass became very fresh. Now, when we look at a little bit further down, when we look at now the dense Labrador seawater layer, we also see that over the years, the dense Labrador seawater became saltier and saltier. And also for the overflow waters, there has been substantial changes. So here I would like to only give you an impression about how dramatic these water mass properties has changed over the past 3 decades. And with that in mind, I would like to move on the overturning estimation. Here again is the map of the North Atlantic Ocean with the 3 hydrographic sections that I introduced earlier. So here what we do is we use these 3 sections and together with ocean boundaries, we build a enclosed box. And then we apply the so-called box inverse method to determine the transports at each of the sections. Because each of the sections are repeated several times throughout the years, so we only group those measurements in the nearby years, and in total we could build 8 inverse boxes covering the period from the beginning of the 1990s to the middle of the 2010s. Now I'd like to first show you the overturning estimation results in the subtropical region. So there are 3 different estimates here. The first one is just the rapid observation in red. The second one is the GECO2 assimilation model estimation. in green, and the black stars with arrow bars are those AMOC estimates from the hydrographic section data. And the thin lines are always the monthly values, and the thick lines are the annual mean values calculated from the monthly time series. And as you could see that all these three estimations agree quite well with each other. And as a reminder that we have shown that the hydrographic properties in subpolar region has changed quite dramatically over the past few decades. And now when we compare the overturning strengths between the different decades, say between the 1990s and 2010s, we do not see a substantially changed AMOC. A similar conclusion can be drawn in the subpolar region as well. In the upper panel, it shows the eastern subpolar basins, and in the lower panel, it shows Labrador Sea, which is the western subpolar basin. The colored line is from the OSNep observation, gray line is still the Gecko 2 AMOC estimation, and the black stars are the hydrography-based estimates. Now, when we compare the different decades, say between the 1990s and 2010s, we do not see a substantially different AMOC. And another conclusion can be drawn in the subpolar region is that when we compare the eastern and western basins, we see that the eastern subpolar basins dominates the total subpolar overturning, and the Labrador Sea only contributes a fraction of the total subpolar overturning. That is consistent with the OSNep observations, and but on a longer scale, on decadal time scales. And finally, we also could say that in the Labrador Sea, Gecko 2 clearly overestimates the AMOC strength calculated from OSNep and inverse results. So overall, we could say that in both subpolar and subtropical region, the overturning was stable on decadal timescales in the past few decades. And as a summary, we first see a dramatic change in water mass properties. However, we do see a relatively stable AMOC since the 1990s, and all these together suggest that overturning changes and hydrographic property change are decoupled to a much higher degree than we previously thought. That's all. Thank you.
That's great. Thanks. Yeah, that's fascinating. I actually don't have any questions myself. I think we have a hand up, and it's Nick. So go ahead, Nick.
Yeah, so great talk. I was curious about relating the AMOC to the property changes at the same location. Don't you need a divergence in the AMOC or the heat transport, I guess, or freshwater flux rather than just the AMOC at one given line in order to relate it to the properties?
Well, that's a good question. I think say if you have a closed box, then you want to estimate the changes in that box. You probably need to give a flux estimates and say you combine different sections. But here, what we try to estimate is basically say in that region, and we use that section to represent the water mass properties in that region. And because there's a very close link between AMOC and water mass distribution, we would generally just expect that they should or they may change at the same time. But what we see is that it is not the case. And actually a related question I get quite often is that so do we also see a compensation, right? Say temperature and salinity compensation, and that is the case in here. So basically, what determines the overturning is basically the density. But when we look at say temperature changes in the same region, basically we see that temperature and salinity are changing in the same direction. So that means the density remains relatively stable in that subpolar region, so that the density and temperature and salinity compensate each other, and we don't see a very dramatic density change to the AMOC was stable.
Great, thanks. Yeah, I agree. And also it's a bit nitpicky of me because you only have certain sections. So I agree that you're kind of limited by the data.
But thank you, that's a great question.
Did you have another, was that a separate question, Nick, in the chat or?
Yeah, there's somebody else who signed in through my name.
Ah, the other
Sorry.
Nick Foukal, yes. Okay, well, so maybe we should just read out the question. Yeah, how did you get velocities for the hydrography-based overturning estimates?
Oh yeah, that's a technical question. So here again, that map, right? So we have the hydrography, and from temperature and salinity, we could calculate the thermal wind relation, right? So we can use the densities to calculate the velocity shears. But of course, that's velocity shear. It's a kind of relative velocity, relative geostrophic velocity. We need to find a reference geostrophic velocity to get the absolute geostrophic velocity, so that the absolute transport. So here, the so-called box inverse method works in this way. So we have first the thermal wind relation, but we then use the different sections and then build the box, and then we conserve the volume of the whole box, and we vertically also divide the box, the water columns, into different layers, and in that way we construct a set of functions, a set of equations. That equations are basically volume conservation equations. We try to use this inverse method to solve those equations to give us a reference velocity set that conserves the total volume in the whole box and in each layer. And yeah, so basically we need to find that particular reference velocity set that satisfies the best to conserve the volume and the volume of the whole box and in different layers.
Great, yeah, thanks, Yao, for the explanation. Okay, oh, I think there was one more question. Is that Isabella? So yeah, go ahead.
Yeah, just following up on that. How close in time are the sections at the different edges of the box, and how does that alias your result, or how can we think about these? Like, are they monthly averages? Are they yearly averages? Are they?
So these are the 6 boxes, 8 boxes that we used. So you see the years. What we try to do is basically we try to combine the measurements that in nearby years, say in 1992 and 1991, 1990, or in the more recent years. So these measurements, of course, that's ship measurements, and that cannot be done at once, and maybe done in different months of a year and different seasons and different years. So what we try to do here is we try to argue that because we first believe that so the measurements in the nearby years should have a water hydrographic condition similar to each other. So we think that's the best way of doing it. And secondly, when we use, say, a measurement in 2011, for example, this box, we use the Ekman transport calculated from the wind. We use the annual mean wind to calculate annual mean Ekman transport. And also, I didn't mention here, but for the subpolar sections, we did use satellite altimetry to constrain the calculation, which is we use the satellite altimetry derived surface geostrophic velocity to constrain the inverse calculation. And for that, we used also the annual mean reference velocity from the satellite. So that in that way, we argue that each of the calculation represents the results from that year. So it's annual mean estimates. In that way, we kind of we kind of minimize the influence of the measurements in different months of the seasons.
Mhm. Great, thank you. Really interesting work.
Thank you.
Isabella, you should step right forward and just go ahead. I guess we just want Yao to shut down his screen sharing and
Yeah.
and you're up for the next presentation.
All right. So I'll just get into full screen here. Great.
Yep,
So my
that looks
name's
good.
great. Thank you so much, Al. I'm going to start my timer here. I'm right up against the end of the hour. So my name is Isabela Le Bras. I'm a scientist at the Woods Hole Oceanographic Institution. And today I'll tell you a bit about work in progress, really, that is on boundary current ventilation in the Irvinger Sea. And I have a long list of folks to thank here, colleagues who have really supported me along the way getting this going, as well as NSF, who's supporting the analysis of this data. Okay, so what I'm interested in here is how oxygen and carbon enter the deep North Atlantic in the subpolar. So by now you've seen a map like the one in the top here quite a few times. So we have OSNAP going across the subpolar gyre, and then in green I'm showing where the OOI Irvinger array is. And it's commonly thought that deep convection in the Labrador and Irvinger seas are really important pathways for getting gases into the deep ocean, so mixing down thousands of meters and then flowing southward in the overturning circulation. But we have very few measurements of dissolved gases in this region. And what's particularly ill-constrained is the role of boundary currents. And that's what I'm really interested in, because in order for these gases to get into the deep ocean, they need to be advected away. And a lot of that happens in boundary currents. So in the summer of 2020, I deployed oxygen sensors on existing OSNAP moorings in the Western Irvinger Sea. So this figure shows those OSNAP moorings, which are the CF and M1 moorings, and the OOI moorings are just off of the screen to the east. And everywhere where there's red is where I added an oxygen sensor. And this complements programs that exist already. So there's another NSF-funded program in the Labrador Sea called GoSnap, which has instrumented the existing OSNAP moorings there with oxygen and some carbon sensors, as well as OOI, which has also been measuring oxygen actually from the inception of OOI, which is great. And so next summer 2022, we're going to be getting these data back, and I'm hoping to answer the question, how does oxygen get into the boundary current, or how is the boundary current ventilated? And if you want to read a bit more about these moorings in the Western Irvinger Sea, you can see some of my past publications there. Okay, so just to give a little overview of the evolving picture of how this boundary current system works here. These are sort of hypotheses that I have about it. So I'm showing in the schematic in purple the boundary current. So you should think of that purple as flow going southward along the coast of Greenland here. And then in the blue and green colors, I'm showing density. So you have the very fresh waters that Nick was talking about up here on the shelf, and then saltier water offshore, which sort of makes this density gradient. We've heard about this deep convection in the central Irvinger Sea a little bit. That's what I'm depicting offshore here. With the deep mixed layers, you have this vertical convection that mixes the water vertically. But then something else that I think is going on here is that winds are often in the same direction as the boundary current. Here in the Western Irvinger Sea, northerly winds, and those cause an onshore Ekman transport, which brings some of this denser water over light water and triggers slantwise convection, which can also mix properties downward into the boundary current directly, but doesn't deepen the mixed layer. Instead, it creates a deep low PV layer. So two of the hypotheses that I'm exploring here are related to these phenomena. So one question is, we think this slantwise convection is going on, But does it also mix oxygen down? Is it only mixing PV, or is that a pathway for oxygen into the deep ocean? And then the second question is, we know that this water formed in the central Irvinger Sea is high oxygen. How much of that gets stirred into the boundary current laterally? Okay, so just to tell you a little bit about why I think this slantwise convection is going on here quickly. So if you integrate over the boundary current, integrate in time the heat loss that's going, the heat loss over the boundary current, you get this panel on the right. So there's sort of similar heat loss integrated over time here from 2014 to mid 2018. If instead you look at the buoyancy loss due to this Ekman flux that I was talking about, there's actually a lot more. And on average over the boundary current, it's about 4 times more densification provided by this Ekman flux than you have from air sea forcing. I'm not going to have time to go over this plot in detail at all, but the top panel is showing potential vorticity, and the bottom plot is showing salinity. The black and gray lines are isopycnals, and the stars are where I've identified a slantwise convection event through the wind forcing. And again, it's a bit of a messy plot, but you'll have to take my word for it, that when we have these downfront wind events, we see PV dropping sort of instantaneously, and we see that the water mass structure is affected by this. So again, the question is, we're seeing some evidence of this going on. We're seeing the water mass structure be affected, but is oxygen also being mixed downward, or is it more of just a sort of secondary instability, mixing more locally and along isopycnals and not mixing gases down? Okay, so on to the second hypothesis here about mixing oxygen into the boundary current laterally. We can look at OOI measurements of oxygen in the central Irvinger Sea that I calibrated here. I'm showing oxygen in the background. The purple isopycnals are the isopycnals of Labrador seawater. And what you can see is that there's high oxygen in this Labrador seawater down to great depth pretty much every year. Some of the interannual variability you can see is that the winter of 2015, early 2015, was this huge production year that sort of kicked off convection in the Irvinger Sea again. And then in 2019, this top isopycnal didn't outcrop. So this high oxygen water is actually constrained to the surface. So we can start looking a little bit at how this oxygen might get into the boundary current using thickness. So the top is oxygen concentration integrated between those purple isopycnals. You can see the concentration went way up again in 2015, and every winter it goes up a little bit. We don't have oxygen in the OSNAP side yet. Hopefully we will next summer, but we can start to think about this looking at thickness of the Labrador seawater. So again, thickness increases every winter, particularly here at the beginning in the central Irvinger Sea. And then in the western boundary, you actually see an increase as well in this Labrador seawater layer. So it seems that some of this Labrador seawater is getting in, but it's unclear if it's really an exchange or just a heaving of isopycnals. So I will end there and just leave you with a few takeaways. These new oxygen measurements will shed light on the boundary current ventilation in conjunction with the OOI measurements. So it's great that those OOI oxygen measurements are already there. And some of the hypotheses that we're going to test are whether this direct ventilation occurs via slantwise convection, and gaining a better understanding of this lateral mixing of waters formed by deep convection, ultimately trying to understand how oxygen and carbon get into the deep ocean. Thank you.
Great, thanks, Isabella. We are up against the top of the hour, I guess, but maybe, so we understand if you have to sign off, but we will, those of us who can stay, any questions for Isabella, we can certainly take those. I don't see any right now. Here we go. Nick, go ahead.
Yeah, I'm just wondering about the sort of correlation between all of these. So, I mean, I imagine that there's sort of a low pressure system comes through and it might activate a number of different processes at the same time. How do you disentangle all that?
Yeah, that's a great question. So I think of these as occurring on different timescales. So the low pressure system and the wind forcing would maybe trigger a slantwise convection event in the boundary current immediately. It would also probably contribute to the Labrador seawater formation immediately, but it's going to take a while for that Labrador seawater to actually get into the boundary current. Like that, I think, is a much slower process. So that's what I would think. Yeah.
So Isabella Femke had a question in the chat that was actually along the lines I was thinking as well. She says, in your earlier paper, you mentioned eddies as a mechanism to get convective water into the boundary. Is that still part of what you're thinking here in this work?
Yeah, the short answer is yes. I'm thinking of those as a potential mechanism for this lateral transport of the Labrador seawater into the boundary current. Yeah, I sort of hypothesized that was taking place, but I'm hoping with this new information, we can make a bit more progress on that.
Are there like, what's the most definitive tracer, so to speak? If you see low oxygen, that's indicative. Can you combine that with salinity or something? Is there enough that you could come away with a 2 or 3 parameter tracer, vorticity, oxygen, and salinity or something, where you'd really be confident that they were linked, the boundary and the interior?
Yeah, I think interannual variability helps a lot. So, if we, it was really nice to see that convection stopping in 2019, because then you can be pretty sure that if something has low salinity, low temperature, high oxygen in the Labrador seawater range, that it was probably that sort of link it back to a particular year. So yeah, that's really helpful. I'm learning from my colleagues in biogeochemistry that oxygen is not a conserved tracer, and we do have to worry a little bit about biology interacting with it as well. But the signals are really large here, and like I said, the interannual variability helps a lot.
Yeah, that makes sense. Thanks. Okay, well, to be courteous of everyone's time, we should probably stop there. If we had more time, I was going to go around to the panelists and ask them, what they thought we were doing well and what we should do differently for the observations. So I'll leave that for, send me an email or something if you've got some ideas. We may or may not be able to do anything about it, but you never know. We could talk about it at least. So listen, thanks everybody. This was really great. Good information and good discussion. I appreciate your time. And Darlene, any closing comments before we sign off?
Just to say thank you all so much. It was really jam-packed full of good information. And thank you. We'll share it on the internet and hopefully get more discussion going. Appreciate all of your time.
All right. Thanks, everybody.
Thank you.